Welcome to this talk on arbitrary data manipulation and leakage with CPU zero-day bugs on RISC-V.
Hold on a second. This is a really big claim you make in your title, and you're a researcher, so this probably is technically true, but your exploits don't work in practice. They're like leaking 1 byte per 3 years or something.
That's kind of rude, but let's make a deal, okay?
Yeah, it depends on the deal.
You see this advertisement panel over there.
Yeah, the one that says RISC-V on it?
Yeah, it's RISC-V. So you can now build the most advanced sandbox there, basically software isolation, a sandbox, and I'll break out of it within seconds, like within this talk.
Okay, I like your optimism, but you won't be able to do this. But let's start. Okay, first, if I just run your application bare bones on the hardware, you can just directly access the hardware.
Yeah, I guess that's easy.
Yeah, we will want this, right? Would be too easy for you. So what I will do is I will also add an operating system in between. Then you can no longer directly interact with the hardware, but you have to ask the operating system using a so-called syscall to interact with the hardware on your behalf. And this is implemented by using basically privilege levels. So the operating system runs privileged, and the user space application runs unprivileged.
But then I can just tell the OS to interact with the hardware, right?
Yeah, but I'm not done yet. So I will use an operating system where I have different users with different permissions. And of course, if you're a privileged admin user, you can still tell the operating system, hey, I want to talk to this LED panel and turn on the lights. And it will do it for you. But I will make you as unprivileged as I can. And then the operating system will just deny you any interaction with the hardware.
Yeah, but still, at that point, I can't find out the password, like brute force it in some way, or find some other exploit in sudo, for example. I'm still not convinced that this is everything you have to offer.
Yeah, I can do one more thing, I guess. I can also put you into some container. And with this container, we have additional isolation. And technically, basically, you can't really even see the hardware anymore. And I'm quite positive that you won't be able to break out of this, because then you would first need to exploit the container, right? Somehow get a nice exploit that gets you out of the container, which already would be a nice zero-day to have. But then secondly, you also still then are an unprivileged user, and you need to escalate privileges. And a Linux privilege escalation exploit that gets you to root, quite a nice zero-day. And yeah, if you root, you can tell the operating system to talk to the hardware.
Yeah, I guess this is kind of hard to exploit, but yeah, let me quickly try something here.
Yeah, sure, but probably it won't work. It's a little bit scuffed up. Can you maybe check your code again?
I guess off by 1.
It's still stuck. Yeah, fix it. OK. Nice. So that's actually impressive. I don't know. How did you do that? What kind of magician are you, man?
Well, I'm no magician. I'm a PhD student. My name is Fabian Thomas, and I'm from CISPA, based in Germany. We're basically a big computer security institute. We do research on this topic. And who are you?
Yeah, my name is Lorenz Hetterich, and I'm also a PhD student at CISPA in Germany. And we are both part of the group led by Michael Schwartz. So basically, our research focus is hardware vulnerabilities, but those you can exploit from software, so without requiring physical access to the device.
Yeah, and our most recent discoveries are basically cache warp, which you might have heard about already, and GhostWrite, which we are currently talking about.
So you call this vulnerability, you just showed me GhostWrite, but how does it work?
Yeah, well, you talked about your nice software security isolations there. So I would have to exploit Docker or some container software there, and then I'm still unprivileged, and I need to get root. But with my hardware exploit, I can do something like this. I just go around all your isolations in software.
Okay.
See, this is your world. Like, this is the world of a software exploitation expert. Like, you have multiple obstacles there. You have to jump through them, jump through some hoops, exploit multiple software systems, and then you might have a nice exploit chain, and you can talk to the hardware. But in my world, this looks like this. I can just directly talk to the hardware. I just can go through the obstacle.
OK, but can you give me more technical details, right?
OK, so you probably know about memory isolation. See, process A, this blue one here, can only access the memory contents of process A. And process B can only access the memory contents of process B. like this orange one here. And whenever process B tries to access memory from process A, it gets killed by the operating system. And like that, you can't just read arbitrary data from the system. But GhostWrite, this bug in the CPU, just doesn't trigger this OS exception here, basically.
Okay, so you can write to memory, if I understand it correctly, but how do you interact with the hardware?
Yeah, well, there's one important detail here, and that is that hardware is basically wired to your memory too. So what we can do is we can just write to some memory address and like that turn on the LED like we did here with this exploit.
Okay, this sounds crazy. This must be really, really complicated and probably like hundreds of lines of nice exploitation code. Can you please show me how this works? I want to see your code.
Yeah, well, here it is.
Like, that's it? Honestly, show me the real code.
Yeah, well, this is not the code that draws the advertisement, but this is all you need to write to physical memory.
Okay, that's quite short. Like, let me check what it does. So you're moving around some address, some value, and then probably this VSE 128 instruction that seems to be the important part. And what is this V0 and T0 this instruction uses?
Okay, so these are just registers on RISC-V. So basically, I just tell you where data is stored in your CPU on RISC-V. And yeah, this T0 is basically just the address of where data is moved to by this instruction. And this instruction should basically just move data from these registers into memory.
Ah, okay, then V0 is probably the value that it moves. So you move the R to memory, correct?
Yeah, correct. But there's one catch here. This is a vector unit strided store instruction. So it not only stores this one value, but multiple values at once. So this goes like this. We can basically just store an entire string by executing this one instruction.
Okay, makes sense, but you mentioned this vector thing. Well, what's that?
Ah, okay, sorry, I haven't introduced that. So like vector is basically just the vector you know from math or from computer science, which is just a collection of values. So instead of just moving one character at a time, this instruction basically moves an entire string or even an entire sentence. And here we just move 16 characters. See, like that.
Okay, that makes sense. Probably if you move many things at a time, then it's faster and maybe also more energy efficient, right?
Exactly, that's the point.
Okay, but you showed me this instruction now, and everything seems fine. I don't know, how does this exploit your CPU?
Yes, so this is only how it is supposed to work. Like, let's try what it actually does. So, like, as I said before, we store memory here. So let's put something at this memory address here.
Okay.
So Black Hat US 24, so we can observe any changes here.
Okay, yeah, I'm looking at it. Can you execute it?
Yeah, I'll execute it now. So
did you already run it?
Yes, I executed it.
Yeah, but nothing changed. Weird.
Yeah, weird. That's what I thought as well. So yeah, I figured at some point it might be that this instruction does not store contents to virtual memory, but to physical memory instead.
Huh? Virtual memory, physical memory? What's that? I've only heard about memory.
Ah, okay, sorry. So we talked about memory isolation before.
Yeah, I see it. It's just memory.
Yeah, but this isn't the whole picture. Like, this is what you see here is only the physical memory, like the memory that is wired in your CPU. But then there's also virtual memory, which you basically see as the software engineer. And then you have data structures in your operating system and in your CPU that map from these virtual pages and to physical pages. And GhostWrite maybe just goes around that and directly writes to this physical memory.
Okay, so I understood this correctly. You have this virtual memory, which is basically what I access if I just write code and use some addresses. I write to virtual memory and read from it. And then you have this mapping structure that translated to physical memory, so basically the ones and zeros that are actually stored in DRAM, and then also all the hardware that's wired there, right? And your idea is that it probably just writes to physical without going through the translation of virtual memory.
That's what I think it might be doing.
Okay, can we test that somehow?
Yeah, let's try it. So basically, we can just use the operating system to set up a mapping to this physical page. So this is now not virtual anymore, but physical. And yeah, we can just observe what happens, right?
Okay, yeah, let me check.
So I'll execute it again.
Okay, yes, something did change, but only the V is there. The rest of the string is missing. That's strange.
Yeah, strange, right? But I have a theory here. See, if we move the R and then after that reuse the address all the time, then at the end we only see the V. So this might be what happens.
Yeah, that might be it. But that's really crazy. You can just write directly to the physical memory. You can probably break everything with that. Can I just run it on my laptop? Or even better, just run it in the cloud?
Well, this is not how it works. See, you basically have 3 CPU types. You have your average x86 CPU, that is your laptop, your desktop, AMD and Intel, or your server CPU. Then you have ARM devices. Those are basically mobile devices, or nowadays even these powerful MacBooks. And then you have RISC-V, the third type. And there you have 2 vendors. You have T-Hat and Sci5. And only this vendor T-Hat is affected here. And from that vendor, only 1 CPU.
Ah, okay, but if it was just one random obscure CPU that no one uses, we wouldn't be here, right? So what makes this one interesting?
So this is not just a random CPU. It's basically one of the fastest RISC-V CPUs that is out there. It's not as fast as your x86 chips, but we are getting there. We have 4 cores, 2 gigahertz, and we even have this vector extension for power efficiency and speed. And nowadays, these CPUs are even available in the cloud, so you can build your compilation clusters with them. And they are available in laptops.
Ah, okay, I got it. But you keep mentioning this RISC-V thingy. What's that?
Okay, for that, let's go back to instruction set architectures. So CPU types is not how you refer to x86 and ARM and RISC-V. You refer to them as so-called ISAs. This is basically just a document that describes how your CPU should behave, and by that describes just valid programs, legal instructions. And currently, the space is dominated by x86 and ARM, and like that, only a few companies can produce CPUs. So if you want to do that, you have to pay high licensing fees, and even then, you might still be limited in customization, so you can't just do anything with your CPU.
Okay, so that's not really nice. If I want to build a CPU, I have to rely on x86 on ARM. But does RISC-V do something better there?
Yes, so RISC-V basically solves everything there. RISC-V is open and community-driven. That means everyone can contribute there, improve the standard, propose new features like this vector extension. And by that, you don't have any licensing fees. So it's free to use, and everyone can just produce CPUs. And on top of that, it's modern and well-designed, which then also means that you can just easily extend it, like with this vector extension. And that also means that you can build low-power chips where you only implement the base instruction set, and you can then build more capable chips with this vector extension, for example.
Okay, but you mentioned that it's open source. As a manufacturer, if I build such a RISC-V CPU, do I have to open source it and give up all my intellectual property?
Okay, this is not how it works. Only the standard is open source. But if you produce your hardware, you don't have to publish your source code.
But if the source code is public, how do you find these bugs? Where do you even start?
Well, the details are here that the C910 is partially open source. The base instruction set there is open source, but this vector extension is not in this open source code. So GhostWrite is also not in this open source code. But do you know fuzzing?
Yeah, I use fuzzing all the time with my software project. So basically, I just throw some random input at my application and then do this until at some point it might crash. And when it crashes, I can analyze what causes the crash and possibly find a bug, fix it, and it's nice. But for CPUs, I mean, you could maybe execute random instructions, I guess.
Yeah, that's what we are basically doing. So we're just throwing random programs, like random data at the CPU until it crashes at some point. So we just try different inputs, and we found a crash in the CPU.
But do they just crash?
Well, some do, but others don't. So we rely on different technique there. that is differential fuzzing. What we do there is basically we compare the behavior of multiple systems. So for example, take two CPUs here that both implement this RISC-V ISA, so they should basically behave the same. And then we, again, provide this random data, and we just observe the state that the CPU is in after executing this instruction, this program. And then we just check that for multiple inputs, and at some point we might find an input here, an input there that basically changes depending on the CPU. And then we might have found a bug here.
Okay, that's very clever, but I imagine there's more to it, right? Because you have to tightly control the state, which probably isn't easy. And also, if I execute like a random number generating instruction, that won't be the same across CPUs, even if they're in the same state.
Yep, so basically we don't want to bore people here with the details on this, but you can just read our research paper there. But
to be fair, I'm still curious about one more thing. Like if you throw just random inputs at your CPU, I imagine most of them are just illegal programs and you won't find anything interesting, right?
Yeah, okay, that's one detail I want to discuss. So we don't throw random data at the CPU, but we basically use like a grammar-based approach where we take this ISA document and then provide only valid programs to the CPU. And like that, we can just fuzz faster.
Makes sense. And you rendered on multiple CPUs, right?
Yeah, we basically use this fuzzing technique on our entire lab where we have multiple RISC-V.
You're calling this a lab? It looks like a mess to me, but I mean, if it works, don't fix it, right? And with this, you only found GhostWrite, or is there more?
Yeah, okay. We did not only find GhostWrite. See, the C910 is not the only chip that T-Head produces. There's also the C908 and the C906, which I would call the big brother and little sister of the C910. And there we found halt-and-catch-fire instructions.
Halt-and-catch-fire? Do they like set your computer on fire?
Okay, no. They just make your system go stuck. So after that, you have to unplug the power cable, plug it back in, and then the CPU is there again.
Okay, can you show me how this looks?
Yeah, sure. So here on the left, you see this rotating donut just to show that the CPU is still online. And then we run our exploit here. And yeah.
Oh, that's stuck.
Yeah. It's just stuck. The video is still moving, so nothing is faked here. Yeah.
Okay, but that's crazy. So you have all those bugs on the CPUs, and I always thought this hardware would be sane, but not that you have like bugs like GhostWrite, which is a really, really big bug. But it also makes a little bit of sense if you think about it. CPUs nowadays, they're really, really complicated, just like software is, and we also have bugs everywhere in software. But for software, I can just go ahead and push an update, and well, then at some point when the update is done, my bug is gone. But I imagine I can't really do this for CPUs, right? I mean, I have steady hands, but there's like 2 nanometers, 5 nanometers transistors. I can't solder that. So once you push out your CPU, you're basically stuck with it, correct?
Yeah. So there's one thing we can do there, and that is basically microcode. This is what your modern x86 CPU has. That is basically just a simple program that runs in your CPU and does some common tasks. And there we can just update this microcode. Just deploy a new version. You can do that via an OS update, and then the bug is gone. And that worked for some of the worst CPU vulnerabilities.
Okay, but does it also work for the vulnerabilities we talked about? Do the RISC-V cores also have this microcode?
Well, unfortunately, no. They don't have microcodes in this. They are currently simple from this perspective, but there's something else we can do. See, this bug is in this vector extension. And fortunately, we can just disable this vector extension. So what we can do is we take the OS, apply an OS update, and then the OS can just disable this vector extension here, and that is our mitigation, basically. But then the bug is still there, but you can't just get exploited.
But you said the vector things make things faster, so I imagine we have an overhead if you do this, right?
Yeah, we figured that as well, and we tried that, and we found that like disabling this vector extension or just not using it has an overhead of 33%. And by that, you lose around 50% of the instructions on these affected chips, which is basically 50% of features, if you want to say it like that.
Okay, that's not nice, but are these core lookups you found, are they fixable?
Yeah, so for the C908, this halt-and-catch-fire instruction where the CPU is stuck, we can basically apply the same fix, so just disable this vector extension. But there we even see a high overhead of 77%, and again, we just lose these instructions. And for the C906, well, we didn't find any mitigation there.
Okay, so all I can do is basically throw away my chip and buy a new one if I have this and I care about this vulnerability?
Yes, if you care about it, you have to do that.
Okay, so we have all those unfixable CPUs around. That's not great. But these core lookups are cool, but let's go back to GhostWrite. It seems more interesting. You already mentioned that we can write to memory, but can we also somehow read memory?
Yeah, that's possible as well, but it's a bit more involved. But bear with me. So remember when we talked about virtual memory before?
Yeah, sure.
So these mapping tables here, these page tables, they are stored in memory as well. So what we can do with GhostWrite is just patch these tables. So let's do that here. Let's change this page 1 to a page 2. And by that, we change this mapping. And now process A can access the memory of process B. And like that, we can just read it or write to it. And if we change this number here to just anything else in the memory, we can even read the entire memory.
Okay, that sounds fun, but to patch those page tables, you have to know where they are in memory, correct? How do you know this?
Yes, so this is the hard part here, but there's one simple trick we can do, and that is we just fill the entire memory with these page tables, with these mapping data structures. And like that, we have a sufficiently high chance to hit one of these page tables. And yeah.
I guess that makes sense. Can you show me how this exploit works? Right?
Yeah, sure. Let's try it. So basically here on the left, we see an admin user doing an update on the system. For that, the admin has to type in password.
So it's stored in memory, I guess?
Yes, it's stored in memory, so we can basically leak it with this attack. And now we have to fill the memory with these page tables. And since the system has 8 gigabytes, it just takes some time.
Yeah, that's quite slow.
Yeah, it's pretty slow, but let's just take a zip.
Yeah, but it's still not done.
So I guess it's barely finished. Yeah, seems to be finished.
Okay.
And yeah, now we can basically leak physical memory, and there it is. Like, we leak this password here from memory of this process A, or this update process.
I mean, that's nice, but that was really slow, and I imagine it probably is quite stable if you fill most of the memory with these page tables, but if you're unlucky, you might still hit something important, crash the system. That's not nice. Maybe we can do something else. Maybe we can somehow do a privilege escalation exploit, so get from unprivileged user to something privileged. And I think I have a nice idea what we can do, because when you want to execute something that is privileged, you can use the sudo utility. And usually, you have to type in your password to do your authentication. But if you already root, then it doesn't ask you for a password.
Yeah, I guess it makes sense, since then you don't have to evaluate privileges, right?
Yes, but the way it works is it basically asks the kernel about the current user. So it does a syscall, and then the kernel returns the current user. And based on that, it does the decision on whether to require authentication and so on and so forth. But my idea would be if we just GhostWrite, write over the kernel, and make it always return root.
Yeah, I guess that could work, but you're missing one detail here, right? Like, we don't know where the operating system, like the kernel, is stored.
I mean, that's a good point, but since it's loaded so early on boot up, I guess maybe it's just always at the same location.
Yeah, probably it doesn't make sense to move it anywhere else. So
yeah, I mean, we can just try, right?
I guess let's try it. So let me execute this exploit. So currently we are unprivileged, and now I'm running it, and
oh, that was quick.
Yeah, root. Okay, that's quicker than the page table-based exploit. Nice.
Man, exploiting these hardware exploits can really be fun. But I never thought that CPUs would be that broken that you have something like GhostWrite, right? But you probably were really, really lucky with your choice of CPUs, and only those tiered CPUs are affected, correct?
Well, like, GhostWrite is not the only bug that is plaguing CPUs. There is more, and a lot more with like cool logos. This is just a subset of all the attacks we've seen in recent years.
Okay, but that's really, really many. But what do they do? How do they like relate to GhostWrite?
Yeah, okay, let me quickly specify. So this basically all began with like hardware, like physical attacks, where you would attach an oscilloscope to a chip and then basically leak some crypto secret, for example, from this chip with this physical so-called side channel attack.
Mm-hmm.
Then later people found out that you can even change data by, for example, glitching the voltage of the chip, and like that you can just give some if condition, for example, and then get a debug mode on some device.
Yeah, okay, but for all of this I require physical access, and with GhostWrite I don't. Are there also other things that don't require physical access to the device?
Yes, at some point, basically people figured out that you can do these attacks from software as well. So what you can do is you mount a so-called side channel on your CPU caches, and like that leak secrets of some crypto primitives, for example. And then people found out that you can basically change data from software as well. So you might have heard about Rowhammer, which is basically like a physical bug in your DRAM chip, where you can change values in this DRAM chip. So here you can only flip bits. So you can make a 0 go to a 1, or you can make a 1 go to a 0. So you're kind of restricted there, but it's already nice to just change like memory. And then our group also found cache warp, which is basically a different attack. And here we are restricted to resetting memory to an old state.
Okay, so
yeah, I guess currently we were pretty restricted there, but like this all changed in 2017 with researchers finding Meltdown, which is basically a bug in like Intel CPUs, like quite many at that time. And with that, you could basically read arbitrary physical memory. So like the opposite of what we did with GhostWrite. And yeah, one could fix that with OS updates, but the bug is basically still in CPUs.
Okay, but it's quite old, it's fixed already, this never happened again afterwards, right?
Yeah, well, it's Black Hat last year. So this downfall bug is basically just a little bit different, but again, you can just leak data there. So this is still plaguing modern CPUs. But like this gap here at the bottom, where we are pretty restricted with Rowhammer and cache warp, is still not filled. But fortunately, unfortunately, we can now fill this gap with GhostWrite.
Okay, so you showed me Rowhammer and I guess cache warp, which can also write memory, but how do they relate to GhostWrite? Are they faster, slower?
Okay, let me quickly give you a comparison there. So let's start with Rowhammer. Like here you are pretty restricted. You can only flip bits in memory, so change a 0 to a 1 or a 1 to a 0. And speed-wise, Rowhammer isn't that great. Like it can take up to, like you can basically only flip bits per hour, so these attacks just take time. And from practicability perspective, I would say they are not that nice to mount, since it's pretty complicated. With cache warp, that got better. Here we can now reset memory to an old state. So not only bit flips, but reset to an old state. Speed-wise, cache warp is totally fine, but practicability-wise, it's still restricted. Like you can't just write arbitrary data. But with GhostWrite, we don't have any restrictions. We are pretty fast, and practicability-wise, I would say it doesn't get any better than this.
Okay, great. So you found one of the worst CPU bugs in this RISC-V C910 CPUs. But does it mean that RISC-V is just poorly designed if they allow bugs like this to enter your CPU?
Okay, so let me make sure that everyone gets this here. Like RISC-V is great. This is not a bug in RISC-V, not a bug in this vector extension. This is just a bug specific to this one CPU. In fact, RISC-V is great. Everyone should just check that out. And what we can learn from this is basically that quality control is important. So what you should do is you could fuzz your chips, fuzz your software before you deploy it. Or if you have the money and time to do so, do formal verification on at least your hardware. And when this doesn't help and you still have some bug in your CPU, it's nice to have it configurable. So at least least make it so that you can disable some extension and or patch the microcode version, for example.
Okay, but I understand. Unfortunately, we don't have that much time left, and I still want to learn more about these bugs and the research we do. Can you show me where I can read more?
Yeah, sure. That's easy. Like, we published an entire website covering this GhostWrite attack, like with the beginning of this talk, and there you can just read the research paper, like find details on our fuzzing approach, what we skipped in this talk, and you can also find our group, stuff like that. And if you're interested in learning more about these CPU vulnerabilities, I can only recommend you this talk tomorrow afternoon, Microarchitecture Vulnerabilities Past, Present, and Future. There you'll learn more about cache warp, meltdown, Spectre, Rowhammer, and all these attacks.
Great, so I will definitely look on the website and see what you did there in more detail, and also attend the talk, I guess, tomorrow. But now, before we get kicked off the stage and before we can give everyone else the chance to ask questions, let me recap what we've learned today so I didn't get anything wrong. You found a crazy zero-day exploit on these RISC-V CPUs, which basically allows you to write anywhere in physical memory from like as unprivileged as it gets, right? You can be isolated as much as, well, as much as possible. And you can still write to physical memory, escalate your privileges, get full control over the hardware. And even what we didn't show you today, you can even get privilege escalation in exception level 2, which is, or machine mode, which is above the OS. And yeah, you can fix this, but for this you have to disable the vector extension, and this makes your chips quite a bit slower. And apart from GhostWrite, you also showed me that there's more vulnerabilities. There's a lot of these bugs. You found the core lookups, and you also showed me like a slide with a lot of Black Hat talks that presented such vulnerabilities. So I think it's also a striving and still finding new bugs. So it's still a nice research area, right?
Yeah, you pretty much nailed it. Like, but at that point, I would say it's best if now the audience can get to a quick Q&A with us. So yeah, make sure to post any questions. You can just walk up to one of those microphones and ask us anything. But other than that, visit the website.
So I think that they use 0.7 vector extension, and like now everybody's moving to 1. Do you think it has any bearing on this? It's just a plain bug that's like independent of which version they would be running, or is it something that version 1 kind of takes off?
So you mean the version of this vector extension?
RV07 is, I think, what those have, and
yeah.
It was a preliminary, and not 1 is the.
And you mean if that has something to do with this, like, not yet published version?
Well, I'm asking you.
Yeah, okay. So I guess maybe, so let's reiterate often that, since we didn't cover that, that is like in the paper. So basically the C910 has this vector extension in it, and it has like a pre-standard version of it implemented. So at that point, people didn't agree yet on how this vector extension should look like. And it might just be that they like squash this vector extension into the hardware, and like that you might have this bug here, but again, this doesn't have anything to do with the standard as is. Like the standard doesn't say, okay, this instruction should just write to physical memory, obviously.
Yeah, and other instructions work fine, and especially smaller vectors, so it might also be that the bigger vectors are just buggy.
Yeah, might be just some overflow in the CPU design, something like that.
But yeah, we don't have the source code, so we don't know for sure.
Yeah.
Which basically answers my question. So the idea, the question would be, do you have any theory on why this happens? Why the address translation doesn't work correctly in that case?
Yeah, that's basically what our idea is. Like at some point, maybe the address translation fails, and then instead of just erroring out and throwing an exception, the instruction just continues.
Or maybe they also implemented it only for machine mode, where you have the direct access to physical memory, and they just forgot to get rid of it when they decided not to use these big vectors, or we don't really know.
Okay, thanks.
But I guess this like address-based overflow or something could be, since like the instruction reuses this address all the time and only writes this 1 byte. So that's our best guess here.
Yeah, so have you checked, or are you thinking about checking other CPUs implementation of vector extensions? Because it might be tricky just to implement them right.
Yeah. So at that point, there's not that many CPUs that have these vector extensions for RISC-V, but we checked this C908 too, and it doesn't have this bug, but it still has this halt-and-catch-fire instruction. So yeah, I mean, you might be right. It's just hard to implement these extensions, and then you have some errors there in your code.
Right. Thank you. Great talk.
Yeah, okay, sure, go ahead.
For the C910,
Yep.
I do believe you mentioned it was used in the cloud. Couldn't you wrap some operational controls, at least around that usage? In other words, maintain control of the environment it's running in?
Yeah, so it's the cloud instances are mostly bare metal instances, so you have basically full control over the chip, because they don't really support that much virtualization stuff yet, so you can't really do hardware-supported virtualization, and it would be really slow. So they're mostly bare metal instances, so it's hard to fix that in the cloud.
But yeah, basically what they now deploy is just an operating system fix, like what we proposed here, just disabling this vector extension. Of course, this is not the best case for customers, but at that point, I guess you can't do anything else.
Two questions. First, when you mentioned that you were fuzzing the hardware, I wonder how did you detect the GhostWrite problem, because it's not causing crash, and yeah.
Great question. I expected that. So we prepared a slide for that. So basically, how this fuzzer can find it is basically just generate this program here, like this illegally encoded instruction here. Then we give it to the C906 and C910. They both implement this vector extension. And then what you see during fuzzing is that the one CPU says, OK, you should not be able to access this memory. So you see a segmentation fault in user space. And the other CPU just says, OK, it's fine, and does this physical write, which we call GhostWrite.
Yeah, and we first investigated, well, OK, if it doesn't throw a seg fault, maybe it just writes to the virtual memory, but we didn't see it there. And then sometimes the CPU crashed, and we did more investigation from that point.
Cool, yeah. The other question is, have you contacted the vendor about this issue, and what's their response?
Yeah, so we contacted them like half a year ago, like around. And yeah, they're still searching like for mitigation, but at that point, I feel like disabling the vector extension is the only thing they can do. What they said to us is they basically now produce another SoC, like with a new version of this chip. So only this T-head 1520 is affected, but I haven't seen any other SoC around, but they are working on that.
Gotcha, thank you.
All right.
If they implemented the cherry extension, would that have alleviated this issue?
Come again?
Are
Which
you familiar
extension?
with cherry in RISC-V? Pointer tagging and capabilities on.
Yeah, we tried that. Like, you mean physical memory protection, this PMP thing, or just memory tagging?
If they implemented cherries
for
their RISC-V,
yeah.
SoC, would they have been able to prevent this bug which had been accidentally introduced?
Yeah, I guess maybe, but I feel like at that point, like this PMP, physical memory protection, would have been like better there. Like what you can do there is basically at least tell the higher privilege levels, for example, the operating system or your like bootloader, like machine mode code, at least protect that from GhostWrite. So.
Because I guess even cherry couldn't completely protect against it. It would just merely limit the range which pointers can access out because of the extra tagging information.
Yeah, maybe you are right on that, but then it could also be that the hardware strips that away on this illegally encoded instruction. So
it depends on how if the instruction is still buggily implemented, it might still go around it and just directly access the physical memory. So it depends on how the bug is implemented in the hardware.
Right. Yeah, especially if it's at the machine level rather than ISO level. Okay, thanks.
Okay, so is it possible to detect the arbitrary write if you don't have different output between the two CPUs? Do you have any idea how to detect this?
So it's pretty hard. The lucky thing here is that when you write like over your OS, for example, then you crash the system. So that's a different way of finding this bug. But yeah, other than that, I guess if it's restricted to only one memory area that doesn't crash the system, it's pretty hard to detect, but yeah.
Thank you.
Right.
You mentioned that you use a grammar to generate your legal programs. When you're using that for your fuzzing, are you writing programs that you know unexpected output should be, or are you just using differential analysis to determine inconsistent behavior?
Yes, so basically we just rely on this differential point, which is also great since then you don't need like a golden model that implements this vector extension in this pre-standard version. And like that you can just differentially fuzz any chip there, at least if you have two that implement the same extension.
All right. I think we're also starting to run out of time, but you can still join us in the rep room if you have further questions.
Yeah.
And we will go there now.